Okay, we want to show that this expression here is divisible by 6. So we want to prove the first case, which is n equals 0. So that means we want to prove that 6 divides into 0. Well, technically true. 2, we assume case n equals k is true. That is 6 divides into k plus 1, 2k plus 1. Okay, true. Required to prove case n equals k plus 1, i.e. that 6 divides into k plus 1, and that will be k plus 1 plus 1, so that's k plus 2, and then that would be 2 times k plus 1, so that's 2k plus 2 plus 1, so plus 3 then. Okay, looks a bit tricky, doesn't it? How far away are we from the previous? So I like that we have k plus 1 here. K plus 2, no, doesn't quite match up, does it? And then, yeah, so what I think I have to do, which I kind of reluctantly don't want to do, is expand this. So that means I need to show that 6 divides into k squared plus 3k plus 2 times 2k plus 3. That means I need to show that 6 divides into, let's multiply by k squared, 2k cubed plus 3k squared, multiplied by 3k, that's 6k squared plus 9k, and then by 2, 4k plus 6. So obviously I like the 6's here. And what would be really nice is if I can easily factorize these 4 pieces back into this. That might be not as bad as I'm thinking. So I need to show that 6 is a factor of 6 k squared plus 1. I just took the 6 out from those two. And then the other 4 pieces all have a k in it, so let's take the k out there. And that leaves me with 2k squared plus 3k, 9k, and 4k is 13k, so that's plus 13. Now I can see that's not quite going to work because there's no way I could factorize this to get this guy here. This 13 is too big. It should be 6 would be better. Six would be better. So I have to do a little bit more cleaning up first. So I'm going to, before I start taking out the 6, I'll just simplify this cubic a little bit more. So that would be 2k cubed plus 9k squared plus 13k plus 6. So I like the 2k cubed because if I take the k out, it'll leave me with 2k squared, which is what I want there. Now, if I take the k out here, I'd be left with 9k. Is that really what I want? No, I want 3k here, so I think I'll change that 9 into 6 plus 3. The 13k, do I want? No, I don't want that. I'd rather have a 1. So I'll change that into 1 plus 12. And I definitely don't want the 6 in there. So, okay. So what I'll do now is I need to show that 6 divides into 2k cubed plus 6k squared plus k. And then after that, in a 3k squared, a 12k, and a 6. So I need to show that 6 divides into, so from the first 3 pieces, I'll just take out k, leaving me with 2k squared plus 6k plus 1. And then from the back, I don't think that's right. Did I put that the wrong way around? Oh yeah, I did. 3 plus 6. So I'll just swap those. 3 here and 6 here. So I'm saying changing 9 into 3 plus 6, and I'll keep 13 as 1 plus 12. Yeah, okay, so just here, just to be clear, the 2x cubed is there, and the 2k cubed is there, 2k cubed. The 9k squared I've split into 3k squared and 6k squared. The 13k I've split into k and 12k, and the 6 I kept at 6. And the whole reason I'm messing about like this is to try and get back to what I had in step 2. So I took out the k here, so that's 2k squared plus 3k plus 1, and then I'll take out the 6 here, k squared plus 2k plus 1, and then I'll factorize, so that will be 2k plus 1 and k plus 1, 2k squared, yep, plus 6 k squared plus 2k plus 1. Right, finally, this one is true from the assumption in 2, and this one is true from having the 6 as a factor. So both of these can be divided by 6, so the sum of them can be divided by 6. So we've proven what we needed to prove in case 3, or step 3. So step 4, 1 plus 2 plus 3 means it's true for n equals 1. Actually, we start at 0 this time. 0, 1, 2, 3, etc. Okay.